This lesson's about energy, specifically three kinds of mechanical energy, kinetic, and two kinds of potential energy, gravitational and elastic. Let's start with just the concept of energy as a whole. Energy really doesn't have a great definition. It's one of those things that we know it when we see it, but we can understand what the forms of energy are and start to make a relationship between them, and that'll help us to know what energy really is a little bit better. So let's zoom in on this slide a little bit. All right, all of these things are different forms of energy. So mechanical energy, things that are moving, sound is a mechanical energy. It's based on the motion of the air molecules and is the focus of what we're going to learn about in a first semester physics course. Thermal energy is something you'll learn about in chemistry, and if you take enough physics, you'll take a class called thermodynamics, where you'll study the transfers of thermal energy. Radiant energy, like light and other forms of electromagnetic radiation, is something that is all around us all of the time. Everybody likes the soft glow of a campfire. You're feeling the radiant energy from that. Electrical energy is something we'll learn about later in physics this semester. Chemical potential energy is something that we learn a lot about in a chemistry class. And of course, nuclear energy. You'll learn more about nuclear energy in both chemistry and if you take modern physics at Ralston Valley, we spend a great deal of time talking about nuclear energy. Now, one way to define energy is that if you have it, you can cause change. If there's a lack of energy, then you can't cause anything to be different. So that's a useful way of thinking about whether or not energy exists. But energy always takes some form, and here are 6. So let's get a little deeper into this part, the mechanical energy. We're going to be talking about 3 forms. One form of kinetic energy, and that's the kinetic energy of a whole object. So let's go to the second slide here. So kinetic energy is the energy associated with motion. Anytime an object is moving, then it has kinetic energy. And the equation to solve for that kinetic energy, so let's think about what this means. E for energy, the K is a subscript, so this kind of energy is kinetic. It's equal to half the mass times the velocity squared. And what that means is, for an object to go a little bit faster, it requires a lot more energy. This is one of the reasons why driving your car really, really fast, you start to get poor gas mileage. It takes more energy to drive faster. Another reason is that friction increases with the square of your speed, so you have to overcome a lot of friction to drive your car fast. Now, the units of this are pretty interesting. So if we think about the units of mass are the kilogram. The units of velocity in the metric system is the meters per second, a meter per second. Since the velocity is squared, the unit of velocity is also squared. And so we get this interesting unit, the kilogram times a meter squared over a second squared. And that has a unique name. It's called the joule, Joules. Don't spell it the other way. It kind of looks bad on you. We abbreviate it with a capital J since it is named after someone. Now, interestingly enough, what we'll find out is every form of energy can be measured in the same unit, regardless of what kind of energy it is. The joule is the standard unit of energy in the metric system. Now, let's do a sample calculation here so we can get a feel for what those calculations might look like. So let's say we had this McLaren F1 and we wanted to know how much energy it has when it's moving at top speed. .38 kilograms, and its top speed is 107 meters per second. So we're going to call that VF because that would be at the end of quite a long acceleration. So if we were going to calculate its kinetic energy at that moment, we would do half times 1138 kilograms times 107 meters per second squared. When we type that into our calculator, we get 0.5 times 1138 times 107. Only the 107 is squared. Come up with this interesting number, 6514481. So that is 6,514,481 joules. We have 3 sig figs in one of these values, 4 in the other, so we'd round this to 3 sig figs. So we'd call it 6.51 times 10 to the 6th joules, about 6.5 million joules. That's that's a big number, and what that tells us is that an individual joule of energy is really small. A joule of energy is not that much energy. Now recognize, if we had, instead of knowing the speed and the mass, if we had known the kinetic energy of the car, and we had known either the mass or the velocity, we could have found the missing value. Because if an object is moving, we know it has kinetic energy. So if we know how much kinetic energy it has, we could work backwards to how fast that mass must be moving. Or if we knew how fast it was moving and the energy, we could calculate what its mass must be. Let's think about at least one of those calculations, how we might rearrange that. This is an important aside here, because if you take a look at our equation sheet, you notice that the equation for kinetic energy is right here, but unlike some of our older units, that is not rearranged anywhere. So this is the first unit in physics this year at Ralston Valley where if you have been dependent on the equation sheet to rearrange equations for you, you're going to need to break that habit. You're going to need to start rearranging equations on your own, and if you know that that's not a particularly strong skill of yours, then rearrange them in advance, put them on a note card, and then you're not scrambling to do it on test or quiz day. So let's say that we knew the mass and the kinetic energy, and what we wanted to know is how fast is it going to go? Well, in that case, let's do this derivation up above the notes. If we know that the kinetic energy is related to half of the mass times the velocity squared, if we knew mass and kinetic energy and want to solve for speed, we need to first isolate the velocity on one side of the equation. So we'd multiply both sides by half times mass. What we'd have at that point is, times 2. Man, every once in a while. We'd have to divide by half the mass, which is like multiplying by 2 and dividing by mass. So let's just do it this way. Divide by half the mass. So divide by half the mass. Sorry for that aside. So we're dividing by a half mass by a half mass. That cancels. If we do the kinetic energy divided by mass on the other side, that's fine, but dividing by a fraction looks a little silly. So instead of dividing by a half, let's multiply by 2. So that becomes 2 times the kinetic energy over the mass equals the speed squared. Now, of course, we don't want to know the speed squared. We want to know what the speed is. So if we square root both sides, then we'd have the square root of something squared. So our equation turns out to be this: the speed of an object is equal to twice however much kinetic energy it has divided by its mass. Again, you can see it takes a lot more energy to go just a little bit faster, since 2ek over mass is squared in the equation. That reflects the fact that it does take exponentially more energy just to go a little bit faster. Now, I'll let you rearrange this equation for mass, but you're welcome to check it with us before test day. So that's kinetic energy in a nutshell. Something's moving, it must have kinetic energy, and it takes some energy from somewhere to give that object its kinetic energy. Now, let's talk about 2 other forms of energy. They're both potential. So we'll go to the next slide, and we're going to start with gravitational potential energy. Gravitational potential energy is energy that's associated with position or configuration. Now, in the case of gravitational potential energy, it's based on position. Things that are up high, that situation means there's gravitational potential energy. Things that are down low don't. This is essentially why if you leave something on top of a hill over long periods of time, you expect it to roll down. Nature tends to end up in a low potential energy state. Water rolls downhill, not uphill. It takes energy actually to create more potential energy. So it takes the energy from the sun to evaporate water to get it up high, but it doesn't take any form of energy to get the water to roll back down. So essentially, potential energy exists because something is up high and it could be pulled back down by gravity. Now, the equation to calculate how much gravitational potential energy exists when something is up high is just simply that mass times ag times its height. So notice we have dy here. So gravitational potential energy only exists when the object is raised up to a particular height. It doesn't matter how it got there. So any motion sideways doesn't change the gravitational potential energy. Only height relates to gravitational potential energy. Now, if you look at this part of the equation, you might notice that that is something else that we know. Mass times the acceleration due to gravity is equal to the force of gravity, which is another word for the weight of an object. We can substitute that in then. Instead of m times ag times dy, since m times ag is the same as the weight, then weight times dy. In other words, weight times height is the gravitational potential energy required to lift something, or the gravitational potential energy that exists once it's there. This is, of course, why I have a picture of a weightlifter here. If there's more mass here on either side, then of course that's going to be harder to lift because it's going to take more energy to lift it, and you're going to have to overcome the weight of the object, how much force gravity pulls down with, in order to lift it. Notice that our units end up being the same. So let's kind of pick it off one at a time. The mass is in kilograms. The acceleration due to gravity is in meters per second. And the distance that you lift it up high would be in meters. When we do the math there, it ends up being kilogram meters squared per second squared. That same friend from the last slide, the joule. So recognize again that this equation can be rearranged. If you knew the energy that existed, we could rearrange that. If we knew what the mass was, we could solve for how high it must be. If we knew the height and how much gravitational potential energy exists, we could rearrange this for mass. The key is, if you see something is up high, you know that the kind of energy that exists is gravitational potential energy, and so you'd want to use this equation to deal with how much gravitational potential energy there is in relationship to how much mass that object has and how high it is. Now let's talk about the other kind of potential energy that is mechanical energy, and that is spring potential energy. So again, potential energy is just energy associated with the position or the configuration of an object. Well, in the case of a spring, it's more about the configuration. So a spring has an equilibrium position where it would typically rest. However long the spring would be typically is its equilibrium position. If we compress it, it can bounce back. Since it can bounce back, that means that it can hold energy. And if we stretch it, it could also bounce back to its equilibrium position. So some springs can only be stretched, some can only be compressed, lots of them can be stretched or compressed, but if something's elastic, sometimes this is called elastic potential energy instead of spring potential energy, and it's stretched or compressed from its typical equilibrium position, then there is energy stored in the configuration of the spring. Since it's stored energy, that's why we call it potential energy. So we abbreviate it in this class capital E for energy, then lowercase sp, spring potential, and it's equal to the average force times distance. Now this is an interesting note, and we're about to take a look at a real spring to get an understanding of it. The further you stretch or compress a spring, the more force it takes. The average force is what goes into this equation. The average force is half of the maximum force required to stretch it as far as you stretched it. So let's take a break from the notes and take a look at an actual spring. So this is a spring scale, and the way that this spring scale works, let me zoom out just a little bit here. The way that the spring scale works, let's zoom way out, you can see the whole thing. You can hold it on this side, and then if somebody pulls on this side, you can actually see inside of this, I'll put my hand behind it so maybe you can see a little bit better, there's a spring that stretches, and the further I pull on this, the more the spring is compressed, or stretched, excuse me, And the less I pull on this, the less the string is compressed. Well, that's frankly how weighing something works. So if we weigh something with a small amount of mass, this is 100 grams, we can see that the force on here it's shown by where this blue disc is. Instead of reading 0, let's focus it a little bit so we can see better. There we go. Instead of reading Instead of reading 0, which it does when nothing's hanging on it, it's reading 1 Newton. That shouldn't surprise us too much because this is 100 grams. 100 grams weighs about 0.981 newtons, about 1 Newton. So notice that how far the spring is stretched. It has to exert a force upwards of 1 Newton to be able to weigh this 1 Newton, in order to lift this 1 Newton mass. Now this is a 2 Newton mass, about 200 grams. And we'll notice that when we weigh the 2 Newton mass, that the spring is much more stretched. And we can see that the indicator is way down here at about 2 Newtons. Here's 1.5, here's 2.5. So the further we stretch a spring, now you can see its equilibrium position where it's not stretched because nothing's hanging from it. The further we stretch a spring, the more force it takes. So since it takes more and more and more and more force to stretch a spring, when we calculate how much energy is stored in the spring when it's stretched, we use the average amount of force. When it's not stretched, the amount of force is 0. When we've stretched it as far as we're going to, that's the maximum force. If we just average the two together, that is the average force to pull the spring that far. Of course, that can be done every time that we deal with a spring. So we have to be thoughtful about what the maximum and the average force was anytime we're dealing with spring potential energy. So we'll deal with that in a lab that we're going to do next week, but we want to give you the heads up now that every time you calculate spring potential energy, it's important to use the average force as you pulled the spring and stretched it, or as you compressed it. Now, let's take a look at the units here. We're going to see again that the units end up being a joule. So force is measured in newtons, distance is measured in meters. Notice this is not dy, it's just the distance that you stretched the spring from its equilibrium position. Newtons is kilogram meters per second, MA. And the Newton meters, well, that's just a meter. Well, kilogram meters squared per second squared, there's our friend the joule. One of the reasons why the unit of energy for all these different forms of energy is the same is because one form of energy can turn into another. You can imagine that if you lifted something up, it would have gravitational potential energy, but of course if you let it go, it would fall, and the gravitational potential energy would go away because it's getting closer to Earth, but that object would get faster, so the gravitational potential energy could turn into kinetic energy as the object falls. You could use something like a slingshot. If you used a slingshot, you'd be storing spring potential energy in the slingshot, right? So here's your slingshot, here's your rock, and you're going to sling it that way. So like the rubber bands that we used in the slingshot during the water balloon activity first semester when we guys got to shoot water balloons at us, the spring potential energy was stored in the elastic bands, and then when the switch slingshot was released, the bands got shorter, so they went back to their equilibrium position, but you shot something out of it, and so the spring potential energy became kinetic energy. So all these units of energy are all the same unit of energy because one form of energy can turn into another. Let's stop there and have you solve some problems about energy.